When I started thinking about replacing the servo motors, I expected it would be a walk in the park. After all, modern servo motors are smaller, more powerful and more efficient, right? That turned out to be slightly optimistic. In this video, we'll walk through the servo motor selection, the choices I've made, the constraints I ran into, and the trade-offs involved. Mounting the motors themselves is a whole different story, and that is for the next video. So let's start with the motors themselves and why this turned out to be more complex than I expected. Here on the bench we've got the original Indramat motor, and next to it the new servo motor I'm planning to use. At first glance, the new motor is a lot smaller. When you look at it, it's much shorter, and it is also a lot lighter than the original. So the intuitive thought is this should make things easier, not harder, right? But that is where reality kicks in. The original Indramat motor has a very specific, almost custom form factor. It doesn't have the same flange mount that NEMA motors do, but instead it uses a bolt hole pattern that no other manufacturer seems to use, at least anymore. And I spent quite some time looking for modern motors with a similar build, but I couldn't find anything that was remotely compatible, let alone affordable. That has honestly been one of the most frustrating parts of this project. You quickly realize how much the original mechanical design locks you into very specific design choices. Another thing that makes this harder is the way the cables are mounted on the motor. As you can see here, the Indramat motor has a very low profile cable connection. On the NEMA compatible motor, the cable connection actually sticks out much further. I won't screw it in entirely because I'll take it off in a second. But when we look at this, it just sticks out a lot further, which is a problem, especially on the current Z-axis. So even though the new motor is smaller, the original mechanical design, which made perfect sense at the time, and in many ways it still does, because it has a nice way to build this motor into the machine, it just becomes one of the main constraints when you start integrating modern components. At that point, it became pretty clear that trying to match the original motor form factor wasn't going to be a realistic path forward. So instead, I made a conscious decision to move away from legacy specific motors and choose a standardized form factor. In my case, that means going with a NEMA style motor. Availability plays a big role here. Standard motors are widely available at reasonable prices, and you're not tied to a single manufacturer or supplier. So this choice reduces vendor lock-in and gives a lot more flexibility going forward. Of course, this isn't a free win because of the things that I already explained before, like the form factor for which I will have to make an adapter, and because of the cable connections that just take up more space. One thing I would like to mention here is that I picked the motor brand fairly early in the process. The main reason for that is that once you start comparing motors from different manufacturers, you quickly run into the fact that everyone specifies things a little bit differently, and locking down the manufacturer early helped me to reduce variables before doing any serious calculations. For this project, I ended up choosing Delta, and that choice was based on a couple of very practical criteria. Price is of course one of them, but local supplier support actually matters more to me personally than price. With my current supplier, if I have a question, I can just pick up the phone and get a quick answer from someone who has years of experience with these motors. And that kind of support is something that I personally value a lot. On top of that, Delta has, in my opinion, very good documentation. Just to put pricing a little bit into perspective, I compared a few 1 kilowatt motors, and on the very low end you can find complete servo kits on places like AliExpress for just over 200 euros. That's a fair price, but I expect the documentation and support to be questionable at best. On the other end of the spectrum, you have the big premium brands. For example, this Onron motor, just a motor, is listed at over 4,000 euros. No drive, no cables, nothing else included. Don't get me wrong, these motors are excellent, but that price simply it doesn't make any sense for this type of retrofit project. Delta sits somewhere in the middle. For a complete setup for the motor, drive, cables and accessories, you're roughly in the 1 to 2,000 euros range. Exact prices aren't public, but any local reseller for these motors can give you a quote. For me, that middle ground turned out to be the best balance between cost, availability, support and documentation for this project. Before going any further, I want to take a small step back and briefly talk about the calculations behind these motor choices. I put all of this into a Kotlin notebook, which I'll link in the description for anyone who wants to dive into the details. At a high level, I looked at things like required torque, the moment of inertia and how that relates to the axis lengths and the moving masses involved. Let's take the z-axis as an example. I assumed the maximum linear acceleration to be 0.5 meters per second squared. From that you can derive the rotational acceleration at the motor. I also estimated the moving mass, the ram, to be about 500 kilograms. It's probably a bit lighter, but it's a rough estimation. Using the dimensions of all the components, that gives a motor side inertia of roughly 1.1 times 10 to the minus 3 kilogram meters squared. From there, you can calculate the torque required just to handle the inertia. To get the full picture, you also need to account for cutting forces. For that, I estimated the cutting force to be about 8 kilonewtons. That's just something I looked up online from several sources. And that ended up to be about 8 kilonewtons. When you combine the torque required for inertia and the torque required for cutting forces, you end up with a total required torque of roughly 4.5 Newton meters. Now, if we look at the motor I selected, which is this one in this column, then we see that it has a rated torque of 4.77 Newton meters, which is a little bit over the required torque. And it has a rotor inertia of, when we convert it to the correct unit of measurement, 0.78 times 10 to the minus 3 kilogram meters squared. That's a very good match with the calculated values. One interesting detail here is the rated speed. I need a speed of about 1500 RPM. And the motor I selected has a rated speed of about 2000 RPM. When I would look at smaller motors, it is typically about 3000 RPM. On paper, that higher speed looks attractive, but in this machine, I don't actually need it. I only need about 1500 RPM. What I need is torque and stability at lower speeds. With a higher speed, you usually end up with less torque at the same power level. Or you have to draw more power to compensate. And that's exactly what happens with the smaller motor options. That smaller motor would have fitted mechanically more easily, especially on the Z-axis, which currently still is the RAM. But electrically and dynamically, it pushes things in the wrong direction. The goal here wasn't to chase exact numbers, but to get a realistic picture of what kind of motor size and power level actually makes sense for this machine. So based on these calculations, I ended up with this specific frame size and power rating, which should give enough margins to stay comfortably within limits. That brings me to one final constraint. At this moment I am currently limited to a 3x16 amp main fuse. In the Netherlands, where I live, that's more or less the maximum you get without your monthly electrical bill increasing significantly. So even if going bigger and faster might look attractive on paper, there's actually a practical electrical limit to what makes sense in this setup. I won't go through all the math in detail here, but if you're interested, the full calculations are available via the link in the description. So to wrap things up, choosing the servomotors turned out to be much more about working with constraints than about picking the biggest and fastest motor. The original machine design, the available electrical power, and practical things like documentation and supplier support all influenced the final choice. The calculations helped a lot, but they're really only part of the entire story. Choosing the motors is one thing. Getting them mounted on this machine is a completely different challenge. And that is what the next video will be about. For now, I'm happy with the choices I've made, even though they've created a new set of problems to solve. But that is also the part of what makes a retrofit project like this very interesting.